Hello and welcome to the Unit 7 podcast on Section 15.1. Today we're going to be introducing solutions. I'm Mr. Sakaguchi,
And I'm Mr. Lin.
and here we go. First thing we're going to talk about are introducing solutions. Remember, solutions are homogeneous mixtures. And remember, homogeneous means that it's a mixture that's uniform throughout, and it can be made up of two or more substances.
So the components of a solution are comprised of two categories, the solute and the solvent. The solvent is usually the part that does the dissolving. You know this as water, usually. The solute is the stuff that is being dissolved, so salt or Kool-Aid powder, sugar.
Um, Solutes and solutions, as well as solvents, can exist either as gases, liquids, or solids, any of the three states of matter. And water is the most common solvent, or the one that we'll be working with the most in class and through some of the problems. A little bit more about some of the terms associated with solutions. If we say something soluble, this is a substance that can dissolve in a solvent. If it's insoluble, this means that it cannot dissolve in the solvent.
If it's specifically just two liquids that we're trying to mix, and they do dissolve, these are known as miscible liquids. Whereas if they do not dissolve in each other, those are called immiscible.
So for miscible liquids, think of things like, for instance, like vinegar and water.
Yeah.
For immiscible, you can think of things like gasoline and water or oil and water.
Or oil and vinaigrette, like salad dressing. That's why you have to shake it.
Like dissolves like, so if we're talking about like dissolves like, polar solvents like polar solutes, and nonpolar solvents like nonpolar solutes. And we'll talk a little bit more about this later in this unit. Solvation, this is a process of surrounding solute particles with solvent particles to form a solution.
So what happens is the interaction between the molecules causes the solute particles to be surrounded by the solvent. And the attractive forces between them causes the solute particles to break apart.
Yeah, so basically, if you kind of look at this figure a little bit more closely, you'll notice that each little solute particle is surrounded by a shell of solvent particles, and this is basically how solvation exists. So notice how the big chunks of salt get broken up into smaller parts, and each one is surrounded.
Now notice also that there are several water molecules per solute particle. In the diagram it shows us very clearly. So it's actually the sum of the attractive solute solvent forces outweigh or are greater than the interaction between the individual solute to solute forces.
That's correct. Good point. There are many attractive forces to kind of keep in mind, and some of these we'll be touching on a little bit more, and some of them we've already talked about in the last previous units. There are ion dipole interactions, so this is the way a lot of our ionic compounds will dissolve. There are hydrogen bonds, and this results in hydrogen being attracted to an unshared pair of electrons from another polar molecule. We can have dipole interactions where polar molecules that are different from each other are attracted to opposite ends. Don't worry about the ion and dipole-induced dipoles. Those are more advanced topics. But dispersion forces is also something we've talked about, where these are basically transient dipoles that occur through the random movement of electrons.
Right, so they're really temporary, and as a result, it's very weak.
But these are the attractive forces that kind of cause the interaction between solute and solvent. So this is touching on some things that we talked about previous. If we're talking about ionic compounds, and it was highlighted in the other slide during solvation, but I wanted to point it out again, and notice how ionic compounds, we talked about how they dissociate, right? And this is what happens during solution if we look at it on the particle level.
If you take a close look at the diagram, you'll notice that the interaction has to do with the opposite charges. So the weak or small negative charge of the oxygen and the positive charge of the sodium are attracted to each other, and that's what causes the sodium to break off from the rest of the ion, and is also shown here with the acetate ion being negatively charged, and then you have your partial positive charge from the hydrogen portion of the water molecule.
And you can see that again, as we said before, each particle gets surrounded by a shell of solvent particles. And you can also imagine you would get to the point, if you kept adding solute, you get to the point where there wouldn't be enough solvent to surround them anymore. And we'll talk about what happens when we get to that point later. With molecular compounds, remember molecular compounds, if they're nonpolar, will not be soluble in water. So only the polar ones actually are.
So this is explaining why oil and water don't mix.
What happens is we get dipole-dipole interactions, and what results is the large molecule will get surrounded by several water molecules. So for instance, I don't know if this is sugar, but let's assume it is, then there'd be many water molecules surrounding the molecule of sugar, resulting in the formation of a solution.
Right.
What affects how fast something, now this is how fast something dissolves. This doesn't mean how much dissolves, how fast. Agitation, which is basically a fancy word for saying stirring.
Or shaking.
Or shaking, or both at the same time. The more you agitate, the greater the rate of solvation occurs.
And what that does is it causes the solvent molecules to be able to interact with more parts of the solute. And this is also done when you increase the surface area. Again, it's just exposing more of the solute to the solvent so that those intermolecular forces get a good grip and start pulling apart the solute.
Right. Imagine if you're making Kool-Aid and you have the big chunk of sugar versus the fine grains. The fine grains tend to dissolve faster than the large chunk does, and that's because you have more surface area available.
Now, the other factor affecting rate of solvation is temperature. Now, the reason this works is because now those solvent molecules are moving more quickly, and as a result, they will pull on those solute molecules with a greater amount of force, and so things will, or molecular motion will increase, and as a result, these solute particles will break apart faster.
Right, so the greater the temperature, the greater the rate of solvation tends to be. Heat of solution, basically there is energy changes with respect to dissolving. Sometimes you'll dissolve something and it'll feel warm, and this is an example of an exothermic heat of solution.
So an example of that would be those hand warmers that you buy at a sporting goods store that you take skiing. You know, you break them apart and shake them and keep them in your pockets to keep your hands or your toes warm.
And then we also have certain solutions that will feel cold because they're absorbing energy from the environment. We call these endothermic heats of solution.
So that would be kind of like those sports packs then.
Yeah, those ice packs where you break it up and it starts to feel cold.
Yeah.
Solubility. As we said before, if each solute particle is getting surrounded by a shell of solvent particles, you're going to eventually get to the point where there isn't enough solvent left to surround the continual addition of solute particles. So you will get to a point where you max out the amount of solute that you can add to form a solution. And this maximum amount is known as solubility. And this is true for a solution made up of a particular solute solvent at a specific temperature and pressure.
Right, so it has to do with what kinds of chemicals are being dissolved in each other. When you max out, that's called a saturated solution, and this can change depending upon the temperature and the pressure.
We also have unsaturated solutions, and that's basically any less than the maximum amount for any given temperature and pressure.
So previously we talked about factors that affected how quickly a solution gets formed or how quickly a solute gets dissolved. Now we're going to take a look at factors that affect how much can be dissolved in our solvent. Two factors, the first one being temperature. Okay, so the higher the temperature, that means that the solvent has more energy and is able to hold up or maintain more of those solute particles floating around inside of it. And if you have a really high temperature and you dissolve a certain amount of solute in it, you can also cool it down, and it's above the critical amount normally. This is called a supersaturated solution, and they tend to be unstable.
Yeah, so supersaturated solutions, they have, as you cool them, they have more than the maximum amount of solute possible. And because of that, they tend to be unstable, and these are things things that we take advantage of to make things like rock candy, for instance. It's a way to grow crystals in solution.
Right. The other factor that affects solubility would be pressure, and this has to do with gases. So this is the bubbles inside your soda. And the higher the pressure that you have pushing down on your solution, the more gas that you will have dissolved inside of it.
This is known as Henry's law in the quantified form. Um, S is solubility in grams per liter, and P is pressure in atmospheres. And we find that they're directly proportional. So S1 over P1 equals S2 over P2.
So the higher the pressure, the more gas the more gas is dissolved, and the lower the pressure, vice versa. Which is why when you open up your bottle of soda, you give it some time, and now it's definitely under much less pressure. The soda eventually goes flat. This is what you're experiencing when you reduce the pressure.
Yeah, what you have to remember is when these sodas are bottled, they're bottled under high pressure. And after you open them, the pressure changes from high pressure to low pressure. And as a result, the solubility drops. So what you initially have is a lot of gas in solution. And because the pressure drops, the solubility drops. And eventually, it goes flat as a result.
Right.
And I think that's it. So we'll see you next time.